Hi, I welcome you all to this session where we are going to see about the basic principles which are involved in the creation of damped and forced oscillations. And taking you along on this journey is Dr. Yunus Jerusha, an assistant professor of physics. This animation clearly shows us how the up and down motion of a spring or the oscillatory motion of a spring is converted in the form of a wave. This is an example of undamped oscillations where the amplitude of the oscillation never decreases with an increase of time. In reality, if a body is set into vibrations, the amplitude keeps decreasing due to the frictional resistance around the body. Let us define this properly. When the amplitude of oscillations of a body decreases gradually with the passage of time due to friction, then such oscillations are said to be damped oscillations. Damping is due to the reduction of amplitude due to external forces like friction, air resistance, and other resistive forces. Along with the decrease in amplitude, the energy of the system also decreases. We now proceed to assign a differential wave equation for damped oscillations and find solutions for the differential wave equation. In order to proceed with that, let us consider a spring in which a body of mass m is attached as shown. There are two forces acting on the spring. There is a force acting in the upward direction and there is a force acting in the downward direction. The force acting in the downward direction is due to the weight which is attached to the spring, and the force which is acting in the upward direction is due to the spring itself. Therefore, this suspended mass is acted upon by two forces. The first force is the restoring force, which always tries to bring back the body to its mean position and is proportional to the displacement. It is denoted by Fr, and Fr is proportional to the displacement small y. And on removing the proportionality sign, we bring in a proportionality constant denoted by small k. Small k has a name, it is called as the spring constant. Therefore, Fr is equal to minus ky. The negative sign is present, indicating that the restoring force is acting in the opposite direction to the downward motion of the mass. The second force acting on the body is the damping force or the frictional force. It is proportional to the velocity acting in the opposite direction of motion. Therefore, Fd, the damping or frictional force, is proportional to dy by dt. The negative sign indicating that this force is acting in the opposite direction. And in order to remove the proportionality sign, we introduce a proportionality constant. This proportionality constant is denoted by R, and R has a name. It's called as a damping constant, or it's called as a frictional force constant. Therefore, the damping or frictional force Fd is equal to minus R dy by dt. If the earlier two forces are acting in the upward direction, there must be a force within the body which acts in the opposite direction, and this force is called as the force of inertia, which a body possesses by virtue of its motion. This force resists a change in the velocity of an object and is given by F proportional to the acceleration d square y by dt square. In order to remove the proportionality sign, we introduce a proportionality constant, the mass of the object, and we have therefore F to be equal to mass into the acceleration d square y by dt square. Under equilibrium conditions, the equation of motion of a body executing damped oscillations is given by m d square y by dt square being equal to the sum of the forces acting in the upward direction. This sum is given by minus ky minus r dy by dt. Ky we saw is due to the restoring force and r dy by dt is due to the frictional force or the damping force. We now divide this equation by m and we have d square y by dt square to be equal to minus k by m y minus r by m dy by dt. The next step, we are going to take these two terms which are there on the RHS over to the LHS, and therefore we have d square y by dt square plus k by m y plus r by m dy by dt equal to 0. Rearrange the equation which we just obtained so that we have the orders of the derivatives in place, and our new equation is therefore d square y by dt square plus r by m dy by dt plus k by m y equal to 0. We substitute for r by m as 2b and for k by m as omega square, and our equation now is d square y by dt square plus 2b dy by dt plus omega square y equal to 0. This we call as equation 1. This is a substitution which we have made for r by m as 2b and k by m as omega square. The solution for this second order differential equation is y is equal to a e power alpha t, where y stands for the displacement, a stands for the amplitude, and this solution we see it is dependent on the time period small t, where a and alpha are arbitrary constants. We differentiate this equation twice and we substitute the derivatives of this y in equation 1 as our next step. So, we obtain the first derivative of y dy by dt to be equal to a alpha e power alpha t. On differentiating this equation again, we have d square y by dt square to be equal to a alpha square e alpha t. We call this to be equation 3. On substituting the values of d square y by dt square and dy by dt represented as equation 3 in equation 1, we have a alpha square e alpha t plus 2b a alpha e alpha t plus omega square a e power alpha t equal to 0. On looking at this equation, it is observed that a e power alpha t occurs in all the three terms and is taken as a common term outside. Therefore, we have now a e power alpha t, in brackets we write alpha square plus 2b alpha plus omega square equal to 0. We all know that a e power alpha t, which is the displacement small y, cannot be equal to 0. Therefore, alpha square plus 2b alpha plus omega square is made equal to 0. You can very well see that this equation is a quadratic equation in alpha, and therefore we can find out the roots of this particular equation. On solving this, we obtain the roots to be minus b plus or minus square root b square minus omega square. On substitution of these two roots in our solution of equation 1, we have small y the displacement to be a1 e power minus b plus square root of b square minus omega square t plus a2 e power minus b minus square root of b square minus omega square t. We denote this by equation 4, and a1 and a2 are the arbitrary constants which have to be found out. Similarly, in equation 4, we see the displacement y is dependent on small b and omega. It is observed from the equation which we just obtained that y the displacement is directly proportional to b as well as omega. By modifying the values of b and omega, we can obtain different types of damped oscillations. The first type of damped oscillation we are going to see is the overdamped oscillation or the deadbeat. This occurs when b square is greater than omega square. When b square is greater than omega square, the displacement will consist of two terms both lying off exponentially to 0 without performing any oscillation. The rate of decrease of displacement is governed by the term minus b plus square root b square minus omega square into t, and the other term is minus b minus square root of b square minus omega square into t. If b square is greater than omega square, b square is greater than omega square, square root of b square minus omega square will be real and it will be less than b. Therefore, this term, this square root term can tend towards 0, and therefore, we will be left out with the exponential term e power minus bt, which is a rapidly decreasing exponential term, and therefore, the displacement is reduced to 0 very quickly without performing any kind of an oscillatory motion, and this type of a motion is called as the overdamped oscillation or the deadbeat. It mostly occurs in a pendulum moving with a very thick coil, or it occurs in a deadbeat moving coil galvanometer. This is an animation showing us the overdamped oscillation or the deadbeat. It is very clearly observed that there is a rapid decrease in the displacement with time. We consider another case where we have b square to be equal to omega square. Therefore, square root of b square minus omega square, which we assume to be small k, tends approximately to 0. Therefore, equation 4 reduces to small y is equal to a1 exponential minus b plus k into t plus a2 exponential of minus b minus k into t. We take t inside the braces and we have a1 e power minus bt plus kt plus a2 e power minus bt minus kt. We split the single exponential term, this term also, into two exponentials in the next step. Therefore, we have now a1 e power minus bt e power kt plus a2 e power minus bt e power minus kt. E power minus bt is common for both the terms. Therefore, in the next step, it is taken out. On taking e power minus bt outside, inside the bracket, therefore, we have a1 e power kt plus a2 e power minus kt. E power kt and e power minus kt are now expanded, and we have in our next step e power minus bt into a1, and this expanded set of terms is nothing but e power kt. E power kt is 1 plus kt the whole square plus kt the whole cube and so on. E power minus kt is 1 minus kt plus kt the whole square minus kt the whole cube and so on. Therefore, this second term a2 e power minus kt is a2 into 1 minus kt plus the rest of the terms for the exponential e power minus kt. We ignore the higher order kt terms and therefore we now have small y to be equal to e power minus bt a1 plus a2. a1 plus a2 are the coefficients of 1 here as well as here, and the second term which we have here has been obtained as the coefficient of the kt term. So, for the kt term here a1 is the coefficient and for the kt term here minus a2 is the coefficient. Therefore, we have small y to be e power minus bt a1 plus a2 plus kt a1 minus a2. We now substitute a1 plus a2 with another term and a1 minus a2 with another term. Let's see what it is. We have substituted a1 plus a2 as small p and a1 minus a2 as q. Therefore, we obtain the displacement y to be equal to e power minus bt, an exponential term, and p plus qt, which is a linear term. This we represent as equation 5. The solution for a critically damped oscillation is y is equal to e power minus bt into p plus qt. Y linearly increases due to the p plus qt term. Simultaneously, y rapidly decreases due to the exponential term e power minus bt. Therefore, y rapidly tends to 0 as t increases. Such an oscillation is called as a critically damped oscillation. It is observed from this animation that the oscillator rapidly decreases in its amplitude with time. When b square is less than omega square, we obtain another oscillation called as the underdamped oscillation. When this less value of b square is substituted in the square root of b square minus omega square, we obtain an imaginary value I beta, where beta is square root of omega square minus b square. On substitution of this in equation 4, we have the displacement y to be a1 exponential minus b plus I beta t plus a2 exponential minus b minus I beta into t. This we call as equation 6. In the next step, t is taken on the inside and we split this exponential as well as this exponential into two exponential terms. Therefore, small y turns out to be a1 e power minus bt e power I beta t plus a2 e power minus bt e power minus I beta t. E power minus bt is common for both the terms present and therefore it's taken out, and inside the braces we have a1 e power I beta t plus a2 e power minus I beta t. E power I beta t and e power minus I beta t can be expanded and written in the form of cosine and sine terms. Therefore, in our next step, we have e power I beta t to be written as cos beta t plus I sine beta t, and e power minus I beta t is written as cos beta t minus I sine beta t. the coefficients of cos beta t and I sin beta t are clubbed together, and we have small y now to be e power minus bt into a1 plus a2, which are the coefficients of cos beta t in the above equation, plus I a1 minus a2 sin beta t. a1 minus a2 is the coefficient of I sin beta t in the above equation. We now denote a1 plus a2 with a sin phi and a1 minus a2 as a cos phi. The equation for y, which is e power minus bt a sin phi cos beta t plus a cos phi sin beta t, is an expanded form of y is equal to e power minus bt a sin beta t plus phi. This is just like the common formula we know for sin a plus b. We now substitute for beta as square root of omega square minus b square. It is observed from this equation we have two terms. One term is a rapidly decreasing e power minus bt term, and then we have an oscillating term, a sine term. Therefore, y continuously decreases due to the presence of the damping factor e power minus bt, and the amplitude will vary from a e power minus bt to minus a e power minus bt. Such type of a motion is called as an underdamped motion, and it is observed in a simple pendulum which is hung in air, and also in the motion of the coil in a ballistic galvanometer. The animation shows that we have a sinusoidal wave, but the amplitude of the sinusoidal wave continuously decreases with time. From the figure shown here, it is very well observed that there is a contribution from the exponential term given by this curve. This is the curve for a e power minus bt, and we have a similar curve below. This is the contribution from minus a e power minus bt. We also have the sinusoidal contribution. The sinusoidal contribution is observed to continuously keep decreasing in its amplitude and is always lying within the envelope of the decaying exponential. The animation shown here is a comparison of the free and the damped oscillations. The free oscillations is observed to be steady as time progresses, whereas the damped oscillation contribution, which is the blue colored waveform, is observed to continuously decrease with an increase of time. The three oscillations, the overdamped oscillation, critically damped oscillation and the underdamped oscillations, are shown in this picture. The overdamped oscillations are seen to rapidly decrease with time, whereas the critically damped oscillation is shown to decrease due to the presence of the exponential term, and there is a slight linear increase due to the linear term p plus qt, which is present in the expression for the displacement. And looking at the curve for the underdamped oscillation, the waveform for the underdamped oscillation lies within the envelope of the decaying exponential curve, which is shown in the dotted line. The next type of oscillation we are going to see is the forced oscillation. When a body oscillates under the influence of an external periodic force, Its oscillations are not with its own natural frequency, but with the frequency of the external periodic force. Such types of oscillations are said to be forced oscillations. We now proceed to obtain the differential wave equation which governs these forced oscillations and its solution. Let us consider a spring which is connected to a mass m. This mass m is acted upon by three forces. The first force is the restoring force, which tries to bring the system back to its equilibrium position and is proportional to the displacement y. Therefore, the restoring force is given by Fr is equal to minus Ky, where K stands for the force constant or the spring constant. The second force acting on the mass is the resisting or the frictional force. It acts in an opposite direction and is proportional to the velocity dy by dt. Therefore, the resisting or frictional force Fd is given by minus R dy by dt, where R stands for the frictional force constant. The last force acting on the mass is the external periodic force itself. This is given by F equal to F naught sin Pt, where P stands for the driving force frequency and F naught stands for the amplitude of the applied periodic force. The sum of the three forces is the total force acting on the system, which is given by minus Ky, which is the restoring force, minus R dy by dt, which is the frictional force, and F naught sin Pt, which is the external periodic force. This we call as equation 1. And always this force is balanced by a force called as a force of inertia, which is inherent within the system. This force, the force of inertia, is given by F is equal to md square y by dt square, which we call as equation 2. And for equilibrium to be maintained in the system, we equate equations 1 and 2, and we now have this expression md square y by dt square minus ky minus r dy by dt plus f naught sin pt. We divide the above equation with m, and we have now d square y by dt square minus k by my minus r by m dy by dt plus f naught by m sin pt. Taking the terms which are there on the right hand side to the left hand side and leaving the external force term alone on the RHS, we now have d square y by dt square plus k by my plus r by m dy by dt equal to f naught by m sin pt. We now replace k by m, r by m and f naught by m with other terms. Let's see what they are. So, on replacing k by m, we have 2b, and on replacing r by m, we have omega square, and replacement of f naught by m is with f naught. Equation 3 is a second order differential equation in y, and for a differential equation of that sort, its solution is given by y is equal to a sin pt minus theta. This we call as equation 4, where a stands for the amplitude of the vibrations, theta stands for the angle by which the displacement y lags behind the external force, and in this equation a and theta are constants. We differentiate equation 4, the solution, twice with respect to t. First, on differentiating it once, we have dy by dt to be equal to ap cos pt minus theta. This we represent as equation 5. On differentiating it again, we have d square y by dt square to be equal to minus ap square sin pt minus theta, which we call as equation 6. We substitute equations 5 and 6 in equation 3, and we obtain minus ap square sin pt minus theta plus 2b ap cos pt minus theta plus omega square a sin pt minus theta equal to f naught sin pt. A small modification is done to the sin pt term which is present on the RHS of the equation. We have subtracted theta and added theta to the pt term which is there on the RHS. Therefore, pt minus theta can be considered to be a and theta can be considered to be b. We therefore have sin a plus b, and we know the full form of the equation sin a plus b, which is sin a cos b plus cos a sin b. Substituting appropriately for a and b, we have sin pt minus theta plus theta to be sin pt minus theta cos pt minus theta sin theta. We now substitute this in the equation which is present above, and we have this relation which is displayed. Now, on comparing the coefficients of sin pt minus theta and cos pt minus theta on either side of the above equation, we have equations 7 and 8. Equation 7 is obtained on comparing the coefficients of sin pt minus theta on either side. It is a omega square minus p square equal to f naught cos theta, and comparison of the cos pt minus theta terms on either side of the above equation gives us 2bap equals f naught sin theta. Squaring 7 and 8 and adding them together, we have a square omega square minus p square the whole square plus a square 4b square p square equals f naught square cos square theta plus f naught square sin square theta. Looking at the left hand side of the equation, we have taken a square which is common for both the terms, and on the right hand side we have taken f naught square which is common for both the terms on the right hand side. And on the right hand side inside the brackets we have sin square theta plus cos square theta, which we all know is equal to 1. Therefore, on the RHS we only have F naught square, whereas on the LHS we have A square into omega square minus P square the whole square plus 4B square P square. From this expression we can find out the amplitude of the oscillation A. This is obtained by taking the square root of this equation and rearranging the various terms. Therefore, A turns out to be F naught divided by square root of omega square minus P square the whole square plus 4B square P square, which we call as equation 9. We can also obtain the phase angle theta by dividing equation 8 by equation 7. We therefore have now tan theta to be equal to 2BP divided by omega square minus P square, from which we can obtain theta, the phase angle, as tan inverse 2BP divided by omega square minus P square, which we call as equation 10. We are going to consider 3 cases here by varying the values of the driving frequency. The first case is when the driving frequency is much lower than the natural frequency. In such an instance, the amplitude of oscillation and the phase will change. The amplitude of oscillation A changes as F naught by omega square, which is a constant. This is due to the fact that P square, which is present in the first term in the denominator, is much less than the omega square term. Therefore, we neglect this P square and we are left out with omega square the whole square, and square root of this gives us omega square. The second term here also will be neglected because it contains a P square term which is very small. Therefore, A is going to be a constant given by F naught by omega square. The phase angle theta, which is tan inverse 2BP divided by omega square minus P square, turns out to be tan inverse 0 because P is very small. Since P in the numerator is very small and tends towards 0, it becomes, this entire set of terms turns out to be 0. Therefore, tan inverse 0 gives us 0 degrees, which means that the amplitude of vibration is independent of the frequency of the force, and this amplitude depends on the magnitude of the applied force and the force constant K. Also, theta equal to 0 degrees means that the force and the displacement are always in phase with each other. We consider another case where P is equal to omega, that is, the driving frequency P is equal to the natural frequency omega. Such a condition gives rise to a state called as the resonant frequency state. Here, in the equation for the amplitude, when we substitute P to be equal to omega, the first term in the square root of the denominator disappears and we are left out with the second term 4B square P square. Square root of this second term gives us 2BP. On substituting for 2B as R by M, we have this expression for the amplitude as F naught divided by R by M omega. Rewriting this equation still further, we obtain the amplitude of oscillations to be M F naught divided by R omega, and substituting for M F naught as capital F naught, we have the amplitude of oscillations to be F naught divided by R omega. We also find an expression for the phase angle theta. Theta, in the denominator we have an omega square minus P square term. Substitution of P equal to omega makes the denominator 0, and therefore we have tan inverse infinity, and tan inverse infinity is pi by 2. And the result which we obtained from these calculations is that the amplitude of vibration is directly proportional to the damping involved in the system, and therefore small damping forces give rise to large amplitude of vibrations, and the displacement lags behind the force by a phase angle of pi by 2. There is another case where we have P to be much greater than omega, meaning the driving frequency P is much greater than the natural frequency omega. In such a case, the amplitude of oscillation turns out to be F0 divided by square root of P power 4 plus 4B square P square. The reason why we have P power 4 here is omega square becomes a very small term and omega square is neglected. Therefore, we have P square the whole square, which becomes P power 4. The second term here contains P square, which is much less compared to the P power 4 term. Therefore, P power 4 and square root of it gives us P square, and substituting for F0, we obtain F0 by M P square. In order to obtain the phase angle theta, we make a similar kind of an explanation where omega square is less than P square. Therefore, omega square is neglected. We are left out with 2BP divided by P square. P in the numerator and denominator gets cancelled. We obtain minus 2B divided by P. P being a very big term, we can assume that it tends towards infinity. If P in the denominator tends towards infinity, we will have tan inverse 0, and tan inverse 0 is nothing but pi. Therefore, we can interpret the results we have obtained as that the amplitude goes on decreasing and the phase difference tends towards pi. There are two animations in this picture. The first animation, which is there on the left, is for the forced oscillation having a higher frictional force constant, and therefore the amplitude of oscillation is quite small. Whereas on the animation which is there on the right, the frictional force constant R is quite small, and therefore the amplitude of forced oscillation is quite large. In this session which you've listened, we have studied about the damped oscillations and the forced oscillations. We studied about three types of damped oscillations called as the overdamped oscillations, the critically damped oscillations, and the underdamped oscillations. Under the forced oscillation category, we obtained three different types of oscillations by varying the driving frequency with respect to the natural frequency. Hope you've understood the mathematical concepts behind these two oscillations. Thank you for your patient listening.